All right, so we've covered a lot of ground over the last few videos. We talked about finding fixed points or equilibrium points, which were points where A star equals G of A star if AN plus 1 is calculated by taking G of AN. And we also generalized that to looking at systems of equations. And saw that basically the same setup will work if you just treat everything as a vector. We also looked at stability. And we saw that if G prime of A star is less than 1, then A star is stable. And for systems of equations, it was a little bit harder. What we actually needed to use was the Jacobian matrix to check for stability. If lambda I is less than 1 for all I, where lambda I are the eigenvalues of J evaluated at X star. So the Jacobian matrix evaluated at the fixed point. If that was the case, then X star is stable. Now, there's a whole lot of subtleties to some of the things that we've done. We didn't derive these theorems in an entirely rigorous manner, but we wanted to get an intuitive understanding of why. And the reason is you can think of the eigenvalues of this matrix as growth rates. They tell you how fast the solution is growing in different directions. And so if you find that the growth rate is less than 1, then essentially what we have is a solution that is shrinking towards the fixed point. And if you have growth rates that are greater than 1, then they're moving away. All right, so a lot of ground was covered. Some of these problems can be quite involved. Algebraically, it took a lot of work to actually find the fixed points and check the stability for systems of equations. So although that's, I think, something that would be useful for you, particularly on your projects, it's not something that you're necessarily going to be asked to do under the time constraints of a quiz. But I think it is important to have an understanding of how these types of methods can be applied to a broad class of problems and not just the nice, simple, easy ones that you often will do in a math class, but the types of messy, complicated ones that are used to describe real-world systems. All right, so we will wrap up this batch of videos here. I will be posting one extra video for you that is an overview of how an epidemic model with a little bit more complication thrown into the mix could be used to describe the COVID-19 outbreak and understand some of the different strategies for combating it. That is completely optional, but if you're interested, I would encourage you to check it out, and you can even play around with the model. There's a link in the caption to the video.